Hello, physics folks. Welcome to Chapter 6 Forces 2. Bum, bum, bum. Alright, so this is really a continuation of Chapter 5 in many senses, and except that we're bringing in some other forces, in particular drag forces and circular forces, or centripetal force, as it, whatever that may be, as we'll talk about. So, just a brief overview. These are the main concepts for Chapter 6. Of course, as you found out by now, just about all of the main concepts from the previous chapters play a role in each upcoming chapter, and so I don't restate those. You'll need most of what you've learned already in Chapter 6 in addition to these new ones. These are just the new ones. Alright, so first off, most of what we're doing in Chapter 6 deals with friction. And as you can see, that's really concept 1, 2, 3, and even in a sense 4. And so let's talk a little bit about friction. First off, you see a little picture here. Friction is really just the electromagnetic force for the most part, if not the entire part. And it's the electromagnetic force that's interacting, well, when particles of two materials interact. And my tablet just froze. Let me pause this. Alright, back in business. So anyway, as I was saying, so when you have two surfaces interacting, two different materials, there's atoms, molecules in those materials, and those atoms interact electromagnetically. And so you have repulsions for the most part, but also probably some attractions going on in there. And the overall effect of each, if you add up all of the individual forces from all the bazillions of atoms and molecules, you'll get what is seen as the friction force. So, and then when you're talking about surfaces, there's two types of surfaces, two types of surface interactions. One where the surfaces are not moving relative to each other, and that's what you'll see as static friction, and one where the two surfaces are sliding against each other, and that's what you'll see as kinetic friction, or sliding friction. So the coefficient of friction is written as mu, so you see that here, and if there's a little k next to it, that means it's the coefficient of kinetic friction, or in other words, sliding friction. Kine means, in its broadest sense, motion. Kinematics equations, the equations of motion, etc. Kinetic energy, energy of something that's moving. So mu sub k is a coefficient of sliding friction, and there is only one value of kinetic friction force for each surface interface. So if you have rubber on asphalt for like tires, then there will be a mu k for if those two surfaces are sliding against each other. For example, if your brakes lock. Or another example, if you wood on cheese, maybe, like if you a mouse slides a piece of cheese along the wood floor, trying to hide it and eat it and devour it, then there's a coefficient of friction for those particular two surfaces. And even then, you can change cheeses, right? You could have Gouda cheese, or you could have Swiss cheese, or Monterey Jack. Anyway, each unique surface interaction has its own unique coefficient of kinetic friction. Even then, in the real deal world, even if you have, like, say, wood on metal or something, or go back to the rubber tires on asphalt, different parts of the rubber might be slightly different than others, and even same with the asphalt. Some parts of the asphalt might be slightly different in terms of composition, and so that you could expect that to change over time, and you'll see that looks like this. That's why this is not a nice flat smooth line. The other one is static friction. That's when two surfaces are not moving in relation to each other. And if you ever tried to move something heavy and you have to push really hard to get it to slide, the pushing you do while it's not sliding, you're pushing, it's exerting a force against you to prevent it from sliding, called friction still, but it's static friction. And so mu s is the coefficient of static friction. that value of friction, of the friction force, changes, because if you push gently, it doesn't move. So it has to push against you with the same gentle force. If you increase your force, etc., etc., it will change. I'll go more into that when I talk about this section. So μs gives the maximum value, the maximum friction force before it starts to slide. And in general, the force of friction, F sub F, equals the coefficient of friction, whatever it may be, usually less than 1, but it doesn't have to be, times the normal force. And the normal force is a support force. I can talk more about that when I talk about this concept 3. Drag forces in general, friction is an example of one, so is air resistance or water resistance, basically fluid resistance. Those forces always point in opposite the direction of motion. They're always trying to slow something down. We can use, these forces often depend on velocity, and so in order to solve those equations for what we need to use differential equation calculus to solve the net force equations that are dependent on velocity. And it's not the most intuitive stuff, and most of you might not have seen it yet, but you've got to learn it at this point. Centripetal force is the other force that we're going to talk about, not in as much detail particularly as friction, but still we're going to mention it. Centripetal force is the net force, always. It's not a real force. It comes about because of other forces. Other real forces, such as friction, tension, gravity, etc., these all cause the centripetal force to happen. They all make something move in a circle. And that net force, there could be friction, tension, and gravity all at once acting on something, allowing it to move in a circle. All of those together will make a net force. And that net force is pointing towards the center of the circle. It's the centripetal force. And the equation for that is mv squared over r. So anyway, that's the rough overview. Let's go into each of these in more detail. Number 1. So the coefficient of sliding or kinetic, I should probably put kinetic friction, is written as mu k, and there is one value of kinetic friction force for each surface interface, and that's what you see here. It's one value. No matter how hard you push or pull on something, as long as it's sliding, that force will remain relatively constant. You see it's not perfectly constant because of what I was mentioning earlier. The surfaces are never uniform, exactly uniform all throughout. Otherwise, if they were, then you'd see this nice flat line. But still, on average, it tends to be a pretty consistent force. And you'll notice it's also lower in most cases than the maximum friction force, maximum static friction force, which we'll talk about in a second. So this is no friction, friction static, static friction, static friction. Here's kinetic friction. So you can see here, there's a box. It has gravity pulling it down, a normal force counteracting that so that the box doesn't fly up or down. Those are equal. So net force in the y direction is 0. And then you have a pulling force causing the object to move this way. And friction, as we discussed, opposes that. And so it's going in the opposite direction. So you see here that the applied force is larger than the friction force. And so the net force is still, if you got F here, and a smaller force of friction, kinetic is how I write it. Then the net force is this minus this, or this, F net. And it's still it's still going that way, so there's still a net acceleration. So this thing's going to speed up. Speed up, speed up, speed up. But if you pull with just the right force and it's still sliding, then you can get it to go at a constant velocity. If the forces are equal, your applied force is canceled out by friction, and there is no net acceleration. And so it's just going to go at it was sliding originally, so it's going to stay at that speed. It's not going to slow down or speed up, so it's going to move at a constant velocity. So that's how the force of friction behaves. Kinetic friction, it stays the same. This is the same length as this, irregardless of, oh no, I used it. I won't tell you the story. I don't have time. Doesn't matter how strong the applied force is. It doesn't affect how strong the kinetic friction force is. All right, and that leaves the coefficient of static friction. So this is the coefficient of friction between two objects when they're not sliding, but it's not the coefficient all along here to here. It's the coefficient right at the maximum value, right before it starts to slide. What do I mean by that? Well, let's take a look at the picture here. So if there are no horizontal forces acting on this, then there's no reason for friction to be involved. Friction is a force in opposition to motion. And if there's no motion or attempt at motion in the horizontal direction, there's no friction. But let's say you start to pull a little bit, but you don't pull hard enough for it to slide. Well, friction is going to, something needs to cancel out your pull force so that it doesn't slide, and that force is friction. Notice how the friction force here, static friction, is equal to your applied force. So that might be like right about here on the graph. You pull hard, this is your magnitude of your force, you pull hard but not hard enough for it to slide yet, but still the friction force equals your pull force. Then we go down to part B, or picture B. You pull harder than picture A, so this is a little longer, but this force of friction has increased to compensate and still exactly cancel out your pull force. So again, you still don't slide. That might be right about here. So your pull force has increased, and so has your frictional force. And then finally, you pull just hard enough so that it just barely starts to slide. That's right here. And yet again, your pull force is still equal to your friction force. The mu, that will, if you do force of friction equals mu static Fn, this force of friction is none of these. It is only the maximum force of friction, that static friction you'll get before it starts to slide. That's what this mu s is, because you can see that there's always a normal force that never changes in any picture. Same, because the weight of it doesn't change. So that's never going to change. So that can't make anything zero. So how can you make the force of friction zero? Well, you'd make this coefficient zero. That's meaningless, because you don't need to know. I mean, you know that something's changing from zero to maximum here. So really the only useful part of this graph is the maximum static friction force here, and that's what we use to define mu s. So I don't know if that was confusing or not, but anyway, the value of static friction force changes up to a maximum force, that's this part of the graph, in order to have zero net acceleration. So in all of these cases, there's zero net acceleration because all forces are balanced. So mu s gives a value of the maximum static friction force before sliding. And then once you slide, you'll often notice that something slides, it all of a sudden seems easier to pull. It kind of like gives away. And that's what this drop is. Like, you'll pull, and friction will get higher and higher and higher, and eventually it just can't handle your pull force anymore. It starts to slide, and then the force of kinetic friction is less than the maximum static friction. And I might have time to do this one. Really, the equation for friction is force of friction equals mu Fn. If it's static, if it's not moving, force of friction is mu s Fn, and as you know, this is the maximum force needed to get it to slide. And then force of friction is mu k Fn. This is the force of sliding friction. Normal force is the same for both. Usually this coefficient is higher than this, and you could say this is force of friction static, force of friction kinetic. You don't need that, or not. You don't necessarily need that. But that's really how friction works. It's very simple. What makes some of these problems tricky is finding the normal force. The normal force isn't always straightforward to find, especially if you're pulling at an angle, which you'll see in some sample problems. But I digress. Let me stop here and continue on with concept 4 in the next video. Later.